So now that we've established what contextual effects are and why they're an issue, let's talk about what we can do about them. And we'll also talk a little bit about random slopes and what we can do about those, and that's the other main issue that we need to think about when including level 1 predictors. So as we've discussed, level 1 predictors are confounded by definition. This is because they have variability at level 1 and level 2, so estimating their effect with a single parameter means that the variance that's being accounted for is ambiguous. And this isn't just a conceptual ambiguity, but it's also a computational ambiguity. So what can we do about it? The sort of common answer and a fairly good answer is to get explicit and to explicitly incorporate the cluster means into your model. So what we can do is we can compute the cluster means for each cluster, merge them into our data, and then use those as a separate level 2 predictor. This is a helpful solution, but it's not perfect. And this is worth thinking about now, although this is something that we're going to talk a little bit more in the semester. So it's worth considering why this might not be a 100% perfect solution, and we'll talk about this in class. So to incorporate the cluster means into our model, first we have to calculate them, and we can do this as before with the aggregate function, where we take the mean of sleep at person ID, and this gives us a different data set. So next we need to rename the sleep variable in this new data set while keeping the person ID name the same. And then we merge our new data into our original data. So now in our original data, we get a new column that's a level 2 variable with the cluster mean of sleep for each person. And then we can fit our model with contextual effects, where we have two sleep variables, one for the level 1 sleep and one for the cluster means. So now let's compare the fixed effects in our two models. So this first model is the model that we looked at last time, where it just has the level 1 version of sleep. And then the second model has both the level 1 and contextual effects of the cluster means. And the first thing we note is that the level 1 variable is actually different in both models. And that's because this is actually a hybrid level 1 and level 2 predictor, whereas this is only a level 1 predictor, and this is only a level 2 predictor. Now let's look at our random effects. So when we look at the model that included just the level 1 version of sleep, we see that we have these two variance parameters. And what happens when we incorporate the contextual effect is that the level 2 variance decreases, but the level 1 variance is mostly unchanged. It's a little bit smaller here, but that's probably, again, just a rounding error in the algorithm rather than an actual impact. Because remember, all we've really done is add a level 2 predictor, which can only account for level 2 variance. So that's how we include contextual effects in our model. And now we're going to talk about the other elephant in the room, which is random slopes. So when we have random slopes, or when we have a level 1 predictor, that means that we have a model with not just random intercepts, but we can also have random slopes. And we looked at this a little bit last time, where we were able to compute both a slope and an intercept for the effect of sleep on p-affect for each person. So as before, we still have a sort of conditional cluster mean on our outcome variable, which is what the random intercept is. But now we also have a random unique slope, or a possible random unique slope for each person's variability within cluster variability of sleep on p-affect. So as with contextual effects, this is sort of best assessed and understood visually. And the main difference in what we're going to do here as compared to what we did last time is instead of looking at the average of all the slope and intercept parameters for each person, we're going to look at each one separately. Now, we can't look at all of them. We have too many different clusters for that, so it would just make too crowded of a plot. So we're going to randomly select 40 and just look at those, just as an example of what random slopes looks like. So we're going to start by setting our seed, which means that when we randomly select 40 unique clusters, we select the same 40 each time. This just sets the random number generator, so it's always doing the same thing the next time you run it. Then we're going to run the sample function. And what this does is what it sounds like. It samples from some variable based on some number. So what we're sampling from is the unique person IDs. So we don't want all of the person IDs, because remember, each person ID is repeated several times in our actual data. So we want the unique person IDs, and we want 40 samples without replacement. And that what this is going to be is 40 different unique cluster IDs sampled from our data. And then to subset our actual data based on the samples that we've chosen, we can use this in function and the square brackets. So what this is saying is we want the person IDs that match the person IDs in cluster, and we want to subset our data based on those cluster IDs. And so this is going to be more than 40 rows, but it's going to be all of the observations that match our 40 randomly selected person IDs. So now we're going to do what we did last time, and we're going to plot our results one step at a time, starting with the skeleton. So the main thing that's different here from what we started with before is we have this group equal person ID piece. So this is, remember, this is what this is saying is that we want each piece of our plot to be different based on person. So first we're going to start with just the skeleton as we showed before. So this is just going to give us the X and Y axis. So next we're going to add the individual data points. And so this is just going to include each individual data point for each of the 40 people that we included. And even though we have this group equals person ID element here, it's not going to change anything for this piece because we didn't specify to change the points by color or anything like that, but we could have done that. So here's our individual data points for the 40 people we selected. And so the next thing we're going to do is we're going to add an individual regression line for each person. And so this is where the group equals person ID comes in. So because we included this, now when we include the same bit of code that we included last time, instead of being one general regression line across all the data, it's going to be a regression line grouped by person. And so here we see this is what it looks like. And we could have, if we added a color equals person ID thing, that would have made the points and lines different colors, but that would get pretty messy. It would be hard to tell them apart anyway. So it's not really necessary to do that here. All we really want to see here is that what's going on is that each person has a pretty different looking slope. So you see this person has a very upward slope. Over here we have a person with a downward slope, and we have lots of different slopes everywhere in between. This is called a spaghetti plot, and I'm sure you can figure out why. So then on top of that, I'm just going to add my aesthetic tweaks, scale the x-axis, scale the y-axis, add the labels, and theme APA from Papaja. And that just makes our plot look a little bit nicer. An alternative approach to visualizing this is to instead have an individual plot for each unique person. And this lets you see the within person effects a little bit better for specific people. If there's any specific slopes that you wanted to separate out, this would be a slightly different and better approach. So we're doing this with a facet wrap function in ggplot, which creates separate panels based on a variable. So we start out the same way. We have group equals person ID with our data. Then I'm saying facet wrap tilde person ID. And I'm saying the number of columns is 3. So that means that we're going to group different panels by person ID, and we're going to have 3 different columns of panels. And then the rest of it's largely the same as before. And so this is what it gives us. It gives us a different panel for each person. We have 3 columns of panels. And then you see we have person 16, person 39, person 44, all with different slopes. And so it looks like we have random slopes. So since we have random slopes, the way we can address this in our model is to model the variability in the slopes by person. And we do this by replacing the 1 here, that's to the left of the vertical bar, with the predictors that we want to have random slopes for. You can have more than 1 random slope. For example, with the plus sign, here we just have sleep, so we're modeling sleep plus the contextual effect of sleep. And remember, this is a level 2 variable, so it doesn't get random slopes. And then we have random slopes for sleep. So now we can compare this to the contextual effects model we fit before that only had random intercepts. So we can look and see what's happened to our parameters, and we see that they've changed a bit. not dramatically for the most part, but they have changed a bit. So these are our fixed effects. And now we can look at the random effects as well. So what we see here is that our sigma squared mu, our random intercept variance, has actually jumped up a little bit, but we have the random slopes, and we also get another parameter here, the correlation between the intercepts and slopes. And so before moving on, here's a sort of little bit of a tricky question for this point in the semester, but why do you think this parameter, the random intercepts, is quite a bit larger in the random slopes model than in the random intercepts only model? And if you look back at one of the plots we did already, there you can actually find a hint as to why this would be the case, but this is something that we will talk about more next week. So another way to look at this table is to call as data frame, and so that gives us not just the variance and standard deviation, but now this we get the covariance between the intercepts and slopes. So before, when we printed it, we could only get the standard deviation. Now we get the covariance here, which is just a way of keeping it on the unstandardized scale and standardized scales at the same time. So we parameterize the correlation between the slopes and intercepts as r mu1 mu2, and the covariance as sigma mu1 mu2, and this will always exist for each additional random effect that you add. You're going to get an extra correlation each time you add. You're going to get an extra correlation between each other random effect each time you add an additional random effect. So if we had another random slope, we would get 3 extra correlations, because we would get the correlation between or 3 extra random effects, because we would get the correlation between the random intercepts, the correlations between the random slopes for sleep, and the variance for the additional slopes term. So the last thing we're going to look at here is we can test the significance of the random slope to the likelihood ratio test. And I put a question mark here because, like before, this isn't perfect. Technically, we're still testing the boundary of the variance parameter sigma squared mu1. We're not testing the boundary of the correlation. We are testing the boundary of the random slope variance. And so technically, this is not perfectly chi-square distributed, but the profile confidence interval method is not going to work correctly here. And I set refit equals false, because since we're testing random effects, we can use restricted maximum likelihood. We don't have to refit with full maximum likelihood. And note that our degrees of freedom here are 2, because we're testing both the covariance and the variance of, so this is the variance of the random slopes and the covariance between the random slopes and random intercepts. And we see here it is significant, but again, this is not a perfect test. And if you look, AIC and BIC actually disagree here. The AIC for the full model with random intercepts is lower, but the BIC is actually higher. It's because BIC penalizes extra parameters a bit more.